As you can see, like the flyers that we displayed, there is a big title which is you always wanted to know and you never dare to ask. It's bigger, really better. We're talking about the brain, of course. And a tiny title on the top that I tried to hide to have a lot of people coming, which is a tractography study of the fronto-parietal visuospatial network. So I'm not a chief. I'm going to give a little bit of is bigger, really better. And after that, we'll go through more processes with the visuospatial networks. So let me introduce you to, this is my mother-in-law. So every year, during the year, she collects things about the brain to give it to me for Christmas. This is her way to tell me that she's thinking about me whole year. And this is very cute. And this year, she offered me a magnet. A big brain like that, with written on the bottom, size matters. So this is a picture of my fridge with a magnet in it. And that was pretty interesting because recently we've been working a lot on correlating anatomy with function. So it came to me like, does really size matters in terms of brain function? Well, if we look at the human brain, well, the human brain is approximately 1,350 cube centimeters. And this is not the biggest brain on Earth. So does anybody know who has the biggest brain? Which terrestrial animal has the biggest brain? Any idea? Elephant. That's right. The elephant got the biggest brain. So it's 4,650 cube centimeters. And if you compare the human brain with the elephant brain, you can easily fit a human brain in the frontal lobe of an elephant brain, which is quite impressive. But hold on. I mean, elephants are not sending ship to space or doing mathematics or these kind of things. So there is something wrong here. And the thing which is wrong is like elephant got a much bigger body compared to humans. And if you do like some very smart mathematics, like dividing the size of the brain of a human by its average weight, the average woman and man, anybody feel bad about 70? And you do the same thing for the elephant, which is roughly around 3,000 kilograms. You obtain these two numbers. And if you do a ratio, you realize that the ratio is really different between the elephant brain and the human brain. For the same size, it looks like evolution has been focusing much more on the brain than on the rest of the body in humans compared to elephants. That's probably why we do same shit to space. But if we want to look at differences within our human race, we got to start look at statistics between brains, between the size of the different brains. And one main statistic what we can look at is what is the average weight of a brain. Well, the average weight of a brain is about 1,450 grams. What is interesting is we're not all having this brain. Some people have a lighter brain, and some other people have a brain which is a little bit weighed a little bit more. So you get a confidence interval about that, which is roughly going from 1,100 to 1,500. So that's pretty interesting. So the first thing I've been thinking about doing is taking the brain of the people from my lab and measuring their size and trying to know whether we had a super genius in the lab and we didn't know. And so that's the idea, that here you're going to have a super genius because they got a big brain, and here you got the stupid one because they got a small brain. And I was pretty surprised, like we all like pretty normal. I won't give any within the anyway, that's not very surprising because this is the case. It's been already shown that very famous people can have a big brain or a small brain and still being very famous because they've been smart enough to do interesting things. For example, a very big brain is Jonathan Swift. That's an English writer, I think, from Ireland. He wrote the Gulliver Travel. Very famous for his literature. He had a big brain, a very big brain. So it fits the model. Okay, he's smart, he got a big brain. But on the other hand, it's pretty sad. That's actually Anatole France, a French guy, I know it. Sorry about that. Like a very small brain. And despite that, he's been able to have the Nobel Prize in literature. So, pretty good. Another very famous guy is Albert Einstein. And this guy got the Nobel Prize in physics. We're still working on this equation, and it's like normal-sized brain. So it really looks like the size itself of the whole brain doesn't change anything about how you're going to be successful in your life, how you're going to be considered to be smart. But speaking about Albert Einstein, if you look more carefully at neuroanatomy, at some details, some peculiarity, you can find things. For example, you got this paper about Albert Einstein comparing normal brain with the brain of Albert Einstein that showed that actually the left parietal gyrus of Albert Einstein is much bigger. In particular, the supramarginal gyrus is much bigger in Albert Einstein compared to the other. It's been thought to be related to his amazing ability in mathematics and abstractions, and is what actually made him so famous. So that's interesting. So it looks like experts can have a different brain from non-experts, or at least a part of their brain can be different. So there was an idea that has been developed in other studies, and for example, there is one which I've been always been impressed about, that actually happened here in London. They tried to compare the brain between London taxi drivers and people that are not taxi drivers. London is a very big city, and when you're taking a cab, you're always saying, well, I'm going to this street, this number, and the guy knows, he knows exactly where it is. So, oh, I know, and there is this shop right next to it. That's pretty impressive. So, at Queen Square, people began to do comparisons between these two populations, taxi drivers and non-taxi drivers. And they found this spot here in the hippocampus, showing that you got more hippocampus in taxi drivers compared to non-taxi drivers. But what was even more interesting is if they look at the time as taxi drivers, these people have been having the job of taxi driver, and the size of the posterior hippocampus, see that there is a direct correlation. That means that taxi drivers are not born taxi drivers. They've been learning to be taxi drivers and tuning their neuroanatomy to be good taxi drivers. Unfortunately, here it looks like size matters. You got a bigger hippocampus, you're gonna be better. But they also find the reverse. And the anterior hippocampus got exactly the inverse correlation. So what can we learn from that is it's not the size that matters, but we know that function may reshape neuroanatomy. And this work has been followed by several different papers that have been looking at neuroanatomy and correlation with behavior. Like, for example, the work of Marcos have been looking at the lateralization of the arcuate fasciculus and its correlation with memory. Or the work of Heidi Johanssenberg that look at the microstructure of the white matter in the corpus callosum and the bimanual coordination. Just put microstructure because that was only control, it can't be integrated. Hopefully. And even more recently, like Matthew Dixon have been doing a sexy study about Royal Air Force pilots compared to normal people, and showed that there was a difference in the frontal areas and parietal areas. So it looks pretty interesting. If you're more interested about the correlation between anatomy and function, and you want to have a look at an atlas, we just have an application where we collect all this information for the iPad. So you can just check it out. This is interesting, but today we're going to talk about the visuospatial networks and visuospatial attention, and how being better in visuospatial attention may reshape your brain. So what is visuospatial attention? Basically, it's a brain reconstruction of our visual environment. But there is a lot of information in our visual environment. Like, for example, you can see here this batter trying to bat the ball. He cannot look at everybody around him. He has to focus on the essential. And this implies a preferential allocation of the limited processing to selected event. And this is called attention. So you get the visuospatial reconstruction, and you pointing at things that are interesting with your brain, and this is called attention. If we put that into context, let's imagine you are in the jungle, trying to find your path to civilization. Well, you're pretty much going to explore your environment and find there are people on this way. It may be good if I'm working this way. This is called control goal-directed attention. It's a strategic and voluntary orienting of attention toward visual targets. And if you take people, you ask them to do a task of control visual attention, put them into the scanner, you measure their activity into the brain, you're going to activate a dorsal fronto-parietal network, including the frontal eye field and the intraparietal surface. And the superior parietal lobe. But hold on, what happens if we change a little bit the overall scene? Putting the tiger this way. Well, you're going to behave completely differently, and your attention is going to mainly focus on the tiger there. Just because your brain is optimizing your survival. You may be so focused that you may even not pay attention to the couple of dollar bills that I put like on the other way. So if you do this kind of task into an MRI scanner and you ask the people like just to do this kind of automatic orienting, you will find that they're going to have a much more inferior frontoparietal activation, as you can see here, including the ventral frontal cortex and the frontal parietal. These tasks include all tasks that are involving an unexpected and automatic orienting of attention toward visual target, like a surprise. So, what did I just say? I said there are two networks. One first network, control goal-directed attention. You orient your attention looking for something. And another one, which is much quicker, which is like to react automatically to events that are happening into the visuospatial. What is the neuroanatomy that is supporting this? Well, in postmortem, we don't have that much information. In monkey, we have a gorgeous description of three longitudinal pathways called superior longitudinal fasciculus 1, 2, and 3, connecting the frontal lobe and the parietal lobe. And if we look at the work of Marco Cavani on the frontal-parietal connection, we have mostly very ventral connections, but we don't have dorsal ones. And I've been trying very hard with Marco brushing behind, saying you should find it. It's there. And despite all I tried, that was very hard. I could only find this ventral branch. That was a big problem, as you can see here. You use the word tractography, you try to look at everything which is going from the frontal lobe to the parietal lobe, and you just have a ventral branch. And you start thinking maybe we only have this ventral branch in humans. But actually that's not true. It's just like the method is limited. And to look at this connection, we'll be using a method which is called the tractography, which is mainly pioneered by Marco here. And tractography is looking at the average organization and orientation of the white matter within large voxel of 2 millimeters by 2 millimeters by 2 millimeters. So if you get different population of fibers within this voxel, but what happens, you're just going to look at the main ones. And this is not good to look at the dorsal connection, apparently. Hopefully, I might Flavio Dell'Acqua during my postdoc. He's been working very hard for doing all his thesis and postdoc about solving this problem. And that's what it pretty much did. Like for same brain here, you get like, we don't see very well, but instead of having big balls like indicating the main orientation, now we get like stars looking at different orientation within the same pulsars. And if you do the tractography the same way, you're going to have much more fibers connecting the frontal to the parietal lobe. And you can even try to look at similarities between human and monkeys and see that actually we have 3 branches connecting the frontal and the parietal. That's pretty cool. Let's get back to visuospatial attention. And to do that, we need to extract the projection of those connections. And if you take enough participants, put them all together in the same space, if you average their projection taking only the hand of the streamlines that I'll be showing here, you can actually start to map the projections, the average projection of those tracks. And this is what we did. So we still have the SLF 1, 2, and 3, and we map it, and we compare it with the activation in functional MRI. And roughly what we see that the SLF3 here in violet, in pink, is mainly connecting the automatically oriented attention network, while the SLF1 in light blue here is mainly connecting the control goal-directed attention network. What is doing the SLF2 is probably linking both networks. I mean, that's all about visuospatial attention. You need to communicate between these 2 networks. Otherwise, what happens if one network says, you gotta look at the left and the other one look at the right? I mean, it's a mess. So it looked to work pretty well, and same authors on functional neuroimaging also reported that mainly visuospatial attention is dominant in the right hemisphere. So they showed like higher activation in the right hemisphere compared to the left hemisphere. So empty box sphere activation in the right hemisphere, full box activation in the left hemisphere. So why not? Function will reshape neuroanatomy. We just saw that it might be possible. So let's look at the lateralization of those pathways. And actually we have a lateralization, which is a dorsal-ventral lateralization, with the most dorsal fibers being more symmetrical than the most ventral ones. And the SLF3 was largely dominant in the right hemisphere, while the SLF2 was slightly dominant. So that's good, but that's not a direct link between function and neuroanatomy. So it's just like showing that roughly we're going towards the same direction, but we don't have a clear link between the 2. So how can we measure the dominance of one hemisphere over the other one in the way you can perceive your visuospatial environment? There is a test for that has been developed and studied, and an effect that has been reported by Michel and Marcotte in the review in Neuropsychology of 2000. One of the first to report this effect, but they were the first to collect all the data that were saying this effect exists, this effect doesn't exist, and prove that actually it really exists. So you show your participant a long line of 20 centimeters, and you just have them put a mark in the middle of this line. The thing is, if your right hemisphere is stronger to perceive space compared to your left hemisphere, it's very likely that you can perceive the left side of the line as bigger compared to the right one. And if you perceive this left side of the line as bigger compared to the right one, you get a bisector line in the middle, you can estimate that it is around here. But the truth is, the line is much smaller than that. So you're going to have a repeated surestimation of the middle of the line towards the left of the line. And this is a general effect. This is the truth center. This is a general effect which is reported as pseudo-neglect. The left deviation in the line bisection is usually regarded as a manifestation of an asymmetrical processing of visuospatial information in the normal brain. Just because you have a dominant right hemisphere for visuospatial information. So let's ask our participants that had an MRI scan to do the same task and try to correlate the deviation, the scoring deviation, how much they get towards the left, with the lateralization of these tracks. And what we found that you get a very good correlation between how much your SLF2 is big in the right hemisphere compared to the left, and how much you're going to deviate towards the left of the line. So this is a direct link between anatomy and function. But in this case, it means that if you got a bigger SLF2 in the right hemisphere, your performance is worse. So it's all a matter of equilibrium between your two SLF. So what happens if, for example, we decide just to interrupt suddenly the communication on the SLF2 in the right hemisphere? It's pretty challenging, but this is possible because actually during neurosurgery, you got patients that unfortunately got a tumor in the brain, and instead of going blindly removing the tumor or not looking at the function, usually the neurosurgeon uses electrodes to stimulate a restricted area of the brain to understand whether they are functional or not functional. So basically how it works, the neurosurgeon stimulates an area. If the patient leaves the arm or stops talking, he says, okay, this area is functional, I'm not going to remove it, otherwise I'm going to have a patient that cannot move his arm or cannot talk after the surgery. It's pretty logical, and we try to apply the same thing with the line bisection, asking participants just to bisect the line while we were stimulating the brain. And what would be your expectation? So we interrupt the communication in the right hemisphere on a network which is apparently correlated with the performance in line bisection. What would happen? Any idea? All right. I'm going to tell the story. What happens if you interrupt the communication on this network? If everything is logical, you're going to actually perceive the left side of the line as smaller, and your bisection will be centered here on what you think being the middle of the line. Well, actually, the line is longer, and you're going to have wide deviation in the line bisection. And during the surgery, so we only had 2 patients. We had only the opportunity to stimulate the white matter in only 1 patient. But it did work pretty well. And when you stimulating on the projection of the SLF, you have a deviation, a slight deviation towards the right. But when you stimulate into the white matter, where we think the SLF is, you have a large deviation towards the right, because the reconstruction of space in the left hemisphere and in the left hemisphere by the right hemisphere has been damaged and stopped. So it seems to work on the left deviation, on the right deviation. So let's try to push it further. Okay, size matters in terms of being better or worse, but in terms of connection, we're talking about an asymmetrical volume, but when we're talking about the volume of the track, what can it be? And what does it mean? Why a track would be bigger? Any idea? You're all forbidden to answer this one. Sorry?
Maybe both sides are used more?
Yeah, but the neuroanatomy which is behind. Yeah, that's one possibility. Because there are 3 possibilities. But I didn't put melination first, and that's in the list. So I'm going to start with the first one, which is there are more connections. So you got more axons, so you send more information, and it's going faster because you divide the work on different paths. That's one possibility. And if you send the information among different paths, you're going to process it faster. Another possibility is you have the same amount of axons, but they're just larger. And there are some work on the conduction velocity and the diameter of nerve fibers that shows that the larger your axon, the faster is the conduction. Another possibility is, as Judith says, you got more myelin. And again, there is work on that. So here you can see here on the graph, on red you got myelinated fibers, and on blue you got non-myelinated fibers. And here you got the axonal diameter. So you see the same effect as before, like axonal diameter can influence the speed of conduction. But you see that in the case of myelinated fibers, you can have much faster speed. So again, these three conditions, three reasons of having bigger axon are apparently linking to faster conduction. So if you have faster conduction, that means that you should process visuospatial information faster on the left compared to the right. Let's try. Let's build an experiment that has the same participant to do that. So we used modified personal paradigm. It's pretty simple. So you got a screen, you got a cross in the middle, and you have to detect as fast as possible stars that may appear on the right or on the left box. Simple as that. You do that for 15 minutes. The participants hate you because it's boring, but that's okay. And at the end, what you find a slight difference between the speed for detecting target on the right and the speed for detecting target on the left. This is not a significant difference, but it's still there. Forget that. So 2007, 2008. And let's do exactly the same thing that we did with the line bisection and try to correlate that with the lateralization of our SLF. And what we found is that actually it is correlated. I mean, if you got a bigger right SLF, 2, in particular branch 2, you're going to be faster to detect target on the left. And if you got a bigger SLF 2 on the left hemisphere, you're going to be faster to detect target on the right. So bigger is better. But do you really want to be faster on one side compared to the other, especially when you're driving a car or piloting a flight, a plane, sorry. It's just like, I'm not sure about that. So this would mean that actually the reconstruction of space would occur into the SLF2 here that will link two networks that are here to explore space in two different ways. So what did we learn from this is that like anatomical viability exists between healthy subjects. We've seen that they don't all have an SLF2 which is bigger on the right hemisphere on the left hemisphere. That's why we can correlate. And that function seems to shape or sometimes reshape neuroanatomy. It doesn't look like you're definitely born with this kind of neuroanatomy. You can also change it later. However, compared to what we saw at the beginning, saying brain size matters, the relation between the size of your neuroanatomy and the performance at cognitive tasks is not always that straightforward. So let's go on a further question, like what's going on if you put a lesion inside the system? Like if you break down the system, well, you're gonna have this syndrome which is called visuospatial neglect. And in visuospatial neglect, for example, those are patients like they got a normal vision, the visual cortex is correct, and they don't have any visual defect. But it seems that they're gonna reconstruct solely one half of their visual environment. And if you ask, like for example here, a visuospatial neglect patient just to bar every single line that are on the sheet of paper, is going to remain barring all the lines that are on the right side of the paper, but not on the left. and he sees perfectly well. He's just not paying attention. So there is no allocation of these limited processing resources on the opposite side of the lesion. And many people have been trying to find the neuroanatomical basis of this syndrome. Like you can see the list of papers that have been trying desperately to find the famous small part in the brain that are used to reconstruct space. And if you take all these papers together and you plot it into a brain, you're going to find that actually you get pretty much a fronto-parietal network. And this fronto-parietal network looks pretty like the non-drive stimulus-driven attention network that is shown in functional MRI, and the projection of the SLF3 and the SLF2. So this is just a meta-analysis, but what happens if we try to do it with new patients? So you take your patients, and take exactly 58 patients, like you get 38 that got neglect, you get 20 that don't have neglect. You look carefully at that lesion, and you just look whether this lesion is disconnecting this track or another track, and so on. And you do that for the 58 patients. It's quite boring doing it, but it is work, because at the end you end up with a graph that is showing you in dark gray or black gray, for patients that are neglect, how many of these patients have disconnection, and on light gray, how many have, without neglect, have a disconnection. So to do this analysis, we use an atlas, which is Atlas for Brain Connection, that is coming out soon. So we use this average anatomy to look at the disconnection. And to check whether the method was working, we first started looking at the visual field effect to know whether or not specific disconnection can predict a visual field effect. And hopefully we find a logical result. We found that no tracks predict pretty well the visual field effect. Only one can predict the visual field effect, and that's the disconnection of the optic radiations. Hopefully it's working. It looks like it's working. So we did the same thing, but this time for visuospatial neglect, looking at all the tracks. And from all the tracks, only one track can predict the presence of visuospatial neglect, is a disconnection of the fronto-parietal connections. And after that, we try to do the same kind of analysis, not looking at the behavioral diagnostics that have been given by the neurologist, but just the result of the test. And what we found is the chronic stage patient with disconnection of the fronto-parietal connection going to deviate more towards the right side of the line, and going to omit more targets that are presented on the left side of the visual brain. So it's working. And well, we try to push it a little bit further, trying to understand which branch participates the most with the syndrome of visuospatial neglect, which is like patching because the resolution of the image was not that good. But we found that on average, the SLF2 is a good predictor for the occurrence of visuospatial neglect, the deviation in line bisection, and the left omission in tasks like you see in the video where you have to bar the lines. So again, the SLF2 is everywhere. But something was like sort of annoying here. It's like you don't have 100% of patients that have a disconnection of the SLF2 that actually have neglect. So you get like patients that don't have a disconnection of the SLF2s that have neglect. What's going on? Why do they have neglect? I mean, we have a model, the model should work, and it doesn't work for at least those patients. So I took this patient and tried to overlap them and look at where was a center of lesion of all these patients together. And what I found is like all these patients all included a lesion of the thalamus. And if you zoom here on the thalamus, you're going to find that actually the lesion that is most frequent in the thalamus is a lesion of roughly the medial dorsal nucleus, lateral dorsal nucleus, and the medial dorsal nucleus, lateral dorsal nucleus. And if you use connectivity atlas that have been developed in the past year using probabilistic tractography, you actually find that there should be a disconnection with the premotor area, which doesn't fit what we know about like anatomical work in animals that say that the lateral dorsal nucleus should be connected with the parietal. So whatever, it looks like it's a disconnection either of the frontal lobe or the parietal lobe from the thalamus. So if we want to take a second take-home message, this time for lesion, we say that neglect can occur after a direct fronto-parietal disconnection. Neglect is a visuospatial impairment, as we've seen, as you can see here in the middle, or an indirect fronto-parietal disconnection via the thalamus. What is always amazing is you think you discovered something and you read a paper of Mesulam and you see that he already did it. He already described it. It's just his intuition. He got like, the shoe works this way. And he's right. He's absolutely right. And future question about that would be how the lateralization of the SLF2 may influence for the recovery of neglect. I mean, let's imagine like that's your left hemisphere, which is dominant for neglect, and you get a lesion in the right hemisphere. Would you recover better? I don't know. That's a future question. Or another question, like I would like to resolve if anybody has ideas, it would be like exactly what is the function of the SLF1 and the SLF3? I don't know. And the projection of the different areas of the SLF1 and the SLF3. But I think like the most exciting question that have been raised recently by Stanislavs and Neuron is what is the link between the SLF2 and consciousness? And they've been doing a review of all these studies that have been comparing, like for example, visible world with invisible world in functional neuroimaging. Detected sound versus non-detected sound. And you can see like you're going to have an activation in the primary auditory area for non-detected sound. And you're going to have this activation plus a large frontal-parietal activation for the detected sound. Same thing for the word. Or inhibitory control by visible cue or inhibitory control by invisible cue. That again, when you're conscious, you have frontal-parietal activation. So I think that like trying to target and understand the link between this connection and consciousness would be like the hardest question in the next 5 years. Thank you very much for your attention.